Okay, so today we will start to talk about the transistor, which will be the MOSFET, especially focus on the operation for the MOSFET. So when we talk about the MOSFET, we can consider the different operation based on the difference in the substrate and also the channel design. So first of all, we will talk about the one we call the N-channel enhancement mode MOSFET. So the enhancement mode is basically means that the threshold voltage is larger than 0. So the threshold voltage larger than 0, that's we call as a enhancement mode here. So the basic operation is that we have the first one still have the p-type substrate here, and then we have the source and drain, and then the gate side, and we need to apply the gate voltage VG larger than VTH here. So once we apply the gate voltage larger than threshold voltage, which we will have the electrons inverted in the channel. And furthermore, normally we will apply the source, we connect the source as a grounded, and we will apply the drain bias here. So once we apply drain bias we have a positive bias on the drain side, so we can expect the electron will be moving from the source to the drain and reach to the drain side. So that's a electron flow here. And then normally in the most of the case that we always consider the current flow. So the current flow is the opposite direction of the electron flow. So you have the electron flow out of the drain, but the current flow will be inside the drain. So this will be the current flow here. So therefore we will have the drain current. So therefore the typical IDVG characteristic, which will be, we have the drain current versus gate voltage here. And because of our threshold voltage is larger than 0 volt, so we have a VTH here. And below the threshold voltage, we won't see any current flow, but beyond the threshold voltage, we will start to see the current flow here. So that's our typical IDVG characteristic. And the reason we call the enhancement mode is because we need to apply the larger gate bias, larger than threshold voltage, to enhance the channel carrier, to enhance the channel electron inverted in the channel. So that's why we call it an enhancement mode MOSFET. On the other hand, we will have another one called the depletion mode MOSFET. So in the case with a depletion mode MOSFET, where we have the negative threshold voltage, so the threshold voltage is generally smaller than 0 here. And then the main difference between the enhancement mode and the depletion mode is because of the depletion mode that already have the N-channel. The N-channel is already existed. So we have an N-channel is already existed. So we have the N-channel already existed. Normally is we have a certain like the implantation of the N type. So you will see this is N plus N plus, and then there's already a part of region that also exhibit as N plus, which is mainly due to the intentional implantations here. So the N channel is existing. So therefore, the device is already turned on. If you look at the IDVG characteristic, so this is IDVG characteristic. So we will have the current at the 0 volt. That already have the current because the channel is already existed. So therefore, at the 0 volt, VG equal to 0 volt, the channel is already turned on. It's already existed. But therefore, the main operation condition is that we need to consider how to turn off the channel. So what we usually do is to give a negative bias. We'll start to sweep as a negative bias. As long as the bias is negative enough, then we will start to deplete the channel. So this is our threshold voltage here. So when VG is negative enough, then we can turn off the channel here. So minus VG is needed to turn off the channel. So the turn off also means to deplete the channel. So that's why we call this as a depletion mode here. So that's a main difference between these two. One is enhancement mode, one is depletion mode. And in the most of a case, when we consider for MOSFET, is normally we will consider as an enhancement mode, because normally we don't want to have the current, even we don't give any bias. On the right hand side is a depletion mode. At the VG at the 0 volt, we already have the current. We need to apply negative bias, and sometimes this become a little bit more complicated for the circuit design, and also with considering as a power consumption. So we normally prefer to have an enhancement mode where our threshold voltage is larger than 0 volt, which means at the VG equal to 0 volt, at this point, we don't have any current flow, and the device is completely off. That's good for the lower leakage current and reduce the power consumption. So since we talk about P channel, and for sure that we can expect the same kind of a device where we might also have in the case with the P channel as well. So in the P channel, we will have the P channel enhancement mode, MOSFET, and then also the P channel depletion mode, MOSFET here. So in the case with the P channel enhancement mode, in this case, you need to think about the a little bit opposite operation compared to the N channel device, because in the P channel device, normally what we need to do is we apply the negative gate bias here to invert the holes. So we need to have the holes inverted in the channel, because the substrate is N type. So therefore we need to invert the hole. So that's why we need to apply the negative gate bias enough to induce a hole inverted in the channel. So therefore, if you look at the IDVG characteristic, if you look at IDVG characteristic here, so in the beginning, we won't have any current flow. But after, once we have enough negative voltage, then we will start to turn on our transistor here. So the threshold voltage is negative, but we need to apply an even more negative bias to induce a Hall. So that's our, for the case with our enhancement mode. That's a case for our enhancement mode. So similarly, we also have this p-channel depletion mode device. So in the case the device, the p-channel in here is already existed. The p-channel is already existed. So we have the holes already layered in the p-channel. Therefore, what we need to consider is that we need to apply the positive bias. Positive bias is needed to turn off the channel. So therefore, at the VG equal to 0 volt, we already have the holes. So the current is already there because the holes already existed. So we need to apply the positive bias as larger as possible, start to deplete the channel to turn off the channel, and finally we can switch off the device. So that's our threshold voltage. So this is the case of a depletion mode. So on the left hand side we have the p-channel enhancement mode. On the right hand side we have a p-channel depletion mode. So the operation concept is just very similar to the N channel, but you just need to put it as an opposite thinking, because now as a whole being inverted, so we need to either apply enough negative bias to induce a Hall, or apply the positive bias to deplete the holes here. And for sure that in most of the case, without any specific purpose, most of the consideration will be the p-channel enhancement mode MOSFET. So since we in the end we still need to consider how to have this current voltage relationship, so it would be good to get a little bit more understanding what would be the how is the current versus different voltage here. So therefore in this in the following we will start to illustrate that under the different bias condition, how is the current gradually formation here. So as for an N-channel enhancement MOSFET with a gate to source voltage that is less than threshold voltage, so which means this is a case where we consider our VGS smaller than threshold voltage, So that's a N-channel enhancement MOSFET with a gate source voltage that is less than threshold voltage. And also, at this moment, we consider with only a very small drain to source voltage, which means we apply as a positive small VDS here. The source and substrate or body terminals are held at the ground potential. So we will ground it at the source and also the body as usual. That's a normal operation condition. So with this bias configuration, there's no electrons inversion layer. There's no electron inversion layer. There's no electron inversion layer. And then also one thing, because of right now, this, which is VGS smaller threshold voltage, so we don't have any electron inversion. But one thing should be aware of that is that right now we apply the small drain bias here, and actually consider for this PN junction here, we apply the small VDS on the N side, which means that we try to reverse bias of this PN junction. So the drain to substrate PN junction is under reverse bias. This is under reverse bias. And one thing just we need to keep in mind that for the typical PN junction under reverse bias, which means we should expect it to see the depletion region between this P and N junction. So we should have the depletion region here. This depletion region in the end will play a major role to influence our IV characteristic in MOSFET, because we won't only consider small VDS. In the end, we will also increase the VDS to the certain level. So that's a first bias consideration. So now we will start to think about what happens if we try to gradually increase the gate bias. So next consideration is that once our gate bias is larger than threshold voltage, so which means this is a VGS larger than VT. And also still the same, this is a consideration with a positive VDS here. Because right now, VGS is larger than VT, so we can expect an electron inversion layer can be created, as shown here. So we have an electron inversion layer. That's induced electron inversion layer has been created so that when a small drain voltage is applied, the electron in the inversion layer will flow from source to the positive drain terminal. This is exactly how we already illustrate in the previous slide, that we have the positive bias here, so the electrons will flow from source through the channel and reach to the drain terminal, and this is electron flow. And in the ideal case, we assume that there's no current through the outside to the gate terminal. So that's the ideal case. We assume that there's no current in this region, there's no gate current, but in reality, for sure that we will have a loss we will have the quite obvious gauge lead current, but that will be influence the results. But in here we consider the ideal case. So now we can step by step to get some more analysis of this current versus voltage characteristic. When we consider the small VDS value, so the channel region normally has a characteristic just like a resistor, because this is under small VDS value, so we can consider channel just a kind of another resistors, and have this correlation where our ID is proportional to the VDS. I think that's pretty straightforward, that we can expect that the drain current has a certain proportional, and we consider this proportional factor as a GD here, where GD is defined as a channel conductance. And the channel conductance just 1 over of our resistance. And this channel conductance can be also expressed by this kind of formula, which for sure will be related to our channel width, channel length, will be related to our mobility, and also related to the charge under the channel. I think this is pretty obvious, because if you assume you have the structure, this is a MOSFET, and we have the source and drain, and also the gate, and with one cases where our VGS1 larger than VT. So the electron density, the channel, the charge in this one, the inversion layer charge can be considered as an amount of, like shown me here. But now, if we have another higher bias, so which is VGS2, VGS2 larger than VGS1 larger than VT. Therefore, we can expect to have a more induced inversion charge here. So the inversion layer charge is a function of gate voltage. Therefore, the basic MOS transistor action is a modulation. It's a modulation of the channel conductance by the gate voltage, right? So the drain current is certainly proportional to our VDS, and where we define as this proportional factor as a channel conductance, and then channel conductance is also correlated with these several parameters, where mu is a mobility and Q1 is a magnitude of the inversion layer charge per unit area, which means that the Q1 is related to the magnitude of this inversion layer charge unit per unit. And therefore, with this consideration, if you try to plot the IDVDS, we have IDVDS here, and therefore we should have this correlation where the first one is the VGS1 larger than VT, and second one, if we continue to increase our gate bias, we will see this kind of a trend where this is VGS2 larger than VGS1. And this is a VGS3 larger than VGS2. So that's our ID versus VD. And this is a case where we consider smaller VDS value, and therefore, in this case, we consider as a channel like the resistance. So this is a typical resistance characteristic, and once we increase the gate bias, the amount of the Q1 is increased, so we can see the current is increased faster here. Okay, so now let's just start to a little bit overview what we have been known so far in order to try to construct the full IDVDS characteristic. So the first consideration is that when for sure that the VGS larger than threshold voltage, right? So that's the case where we start to have the inversion channels, inversion charge in the channels. And also, at the first case is that we apply the VDS is small. So for example, like here, we make sure that the VGS is larger than VTH, but we don't apply the large VDS here. So in this case, we will have this channel inversion charge, and as I say that the electron flow will flow from source to the drain. So that's a electron flow, and the drain current is flow from the drain to source, IDS here. So that's the first case where we have a smaller VDS. But now we will be interested in continue to increase our VDS bias. So once the VDS value is increased, the voltage drop across the oxide near the drain terminal decreases. So why decreases? So this is because this is a gate voltage, this is a drain voltage. So therefore, your voltage difference between the gate to drain, VGD, that's very simple, is equal to VGS minus VDS, right? So now we continue to increase our drain bias, so which means the VDS increase. So once the VDS increase based on this simple formula, then VGD decrease, right? So what does this mean? So if you consider as a channel charge density is proportional to our gate bias, from the left to the right, as close to the right as close to the drain terminal, the drain bias is, the VGD is decreased. So the VGD decrease suggests that the channel inversion charge will decrease once close to the drain terminal. So once close to the drain terminal, because of now your voltage drop between the gate to drains becomes smaller. So the amount of inversion charge is always determined by how large of a gate bias here. But once we have the increasing drain bias, so amount of the effective gate bias on this location is decreased. So once it's decreased, so therefore the amount of Q1, the amount of the inversion charge here will be decreased as well. So once this decrease, which means our channel conductance decrease, the channel conductance decrease. So the incremental conductance of a channel at the drain side decreases, which means the slope of the IDVD curve will decrease. So let's rethink about the IDVD characteristic. We have an IDS, we have a VDS characteristic. So in the last slide, we have been shown under the small drain bias, it's a linear correlation which has this kind of a characteristic. So that's in the previous slide. But now the original slope could be something like this one. But because of the VGD is getting smaller because of the increase of drain bias, in the end the slope will decrease as well. So therefore we can expect the IDVD curve could be something become like this one. So the slope, the conductance decrease means the slope decrease. So now we will foresee to see a little bit getting slower increase of ID when increasing VDS. So we will be interested in continue to increase the drain bias and to see what happens. This is one, this is a decrease here. So if you continue to increase the drain bias here, they could be reach a point where potential drop across the outside at this point will become zero. Because right now, as I already say, VGS minus VDS, which is equal to VGD here, and there's a chance that the induced inversion charge density become zero at the drain terminal. Here become zero, and this will be happen when in the end our VGD at the drain terminal, our VGD at the drain terminal will be exactly equal to threshold voltage, because of we only have this inversion charge once the VG is larger than VT. But when the VG is equal to VT, that means we won't have any inversion charge, and therefore the inversion charge at this point will be equal to zero, which means this is a condition VGD is equal to VT, and at this point we call this as a saturation VDS. So when VDS reach as a VDS set here, that would be equal to VGS minus VDS set is equal to VT here. So this means ID VDS, we have ID and VDS. So this means in the beginning it's a linear increase where we already say that's under the small drain bias, but now we start to see a saturate of the slope. So we start to see a saturate of the slope, a decrease of the slope, which become like here. And once at the point where we start to see the inversion charge density is equal to zero, which means this is a bias that the VDS reached to the VDS set. And actually the set, which is an abbreviation of the saturation region. So which means once the VDS is larger than VDS set, then the current will reach to the saturation region, and before the VDS set, which is the linear region. So finally, we will be still very interested in what would be the current correlation when the VD is reached to the saturation region. So now again, that's very important, because now we have to a little bit combine what we have been know from the MOSFET, but also with the PN junctions here. So when VDS become larger than VDS set here, the point in the channel at which the inversion charge is just 0 move towards the source terminal. So that's from the text, it's difficult to understand. So let's just try to explain it step by step. So imagine you have the MOSFET structure. This is a typical MOSFET where we have the source and drain and gate. So that's the source, drain, and gate here. So once we continue to increase the drain bias, then contribution of this reverse PN junction cannot be ignored. So we still have to a little bit remind ourselves that we have the P substrate here. And once our VDS larger than VDS set, we cannot call this as a smaller drain bias anymore. It's actually quite large of the drain bias, which means the amount of the depletion region between this drain to the substrate, which is actually increased. So we can expect we have such wider depletion region can be formed in the drain bias between the drain to substrate when we apply enough high VDS. So therefore, this is the region where we will start to have the wide depletion region, or we call the space charge region. It's the same. So in this case, we will start to see the inversion channel. On the last line, we have the inversion channel here because of the formation of this wide depletion region. So the inversion channel will start to move toward to the source side and then become as shown like here. So that's our inversion channel. So this is actually how this text try to illustrate the point in the channel at this will just move toward the source terminal. So this is actually how this sentence try to illustrate. Original is here at the 0 charge, but now because of due to the depletion region, so this will move toward the source, and this will become here as a 0. That's original 0, but now we have the new position that calls a 0 inversion charge, which is here. So in this case, electron enter the channel at the source. Still, we have the electrons here from the source side. We still enter to the channel, enter the channel at the source, travel through the channel toward the drain, but at the point where the charge goes to 0, so the electron move to here and reach to this point. But then how this electron can travel through to the drain side, and that will be highly determined by the electric field inside this space charge region. So when the charge goes to zero, the electrons are injected into the space charge region. So electrons will injected in the space charge region, and where they are swept by the electric field. Because right now we have the p-n junction here. So we also have to take into account there's internal electric field in this direction. So we have the E field in this direction. So therefore, the electrons first travel to at this point and then will be swept by electric field and reach to the drain side. Finally, still the electron can reach the drain side and become the current here. So, space charge region is already shown in here, and where they are swept by the electric field. To the drain contact. So, in a simple schematic, try to illustrate here. It's the same, and then just use a different simplified schematic. So once the VDS is larger than VDS set here, so we can expect the channel will moving, the 0 point will moving towards the source side. Showing as a triangular here. And then based on our explanation, the electron in the source will first go through this channel, and because of this the 0 point that will moving towards the source side because of formation of the space charge region, and inside the space charge region we will have the electrical field. So therefore, the electrons can be moving to the drain side because of the electric field. So that's how, in the end, the electron can be successfully travel from the source to the drain. And this schematic from the textbook actually is the same from here, but just a little bit simplified. But if you can understand what I'm talking about by using this graph, then that should be no problem for you to understand the whole things here. So finally, we can physically construct the whole IDVD curve. We have a IDS versus a VDS here. So as already shown, we have in the beginning have this from the linear region, and then once reached to the one certain point, that's a VDS set. The current now is determined by the electric field, and then the amount of a charge is actually not that increase anymore. So therefore, you will start to see the saturation of the current. So that's why we call this as a saturation region. And then as I say, this is a region we define as a linear region. So now let's recap a little bit the reason why from the linear to the saturation, why the current will linear increase, the slope decrease, and getting saturated. And this all because of our channel density, our inversion charge layer formation in the channel will become from the beginning as a uniform distribution along the source to drain, and later we will start to see as an increase of the drain bias, then the VGD becomes smaller. So therefore, we will start to see non-uniform of the charge in the channel. And then at this moment, which will become exactly zero at the drain terminal, and beyond this point, we will start to see the channel 0 point of the charge will move away from drain terminal and close to the source side. So now, if you can follow the understanding of this charge formation of these 4 small, like the red cartoon here, if you understand what I'm talking about, these 4 red cartoon, and then you basically understand all the key concept for the MOSFET, how the current will be formed in the end, leading to the linear and saturation of ID-VD characteristic. Okay, so once we have a physics-based understanding for the ID-VD curve, so next one is we want to have a certain the solid equation that can help us to get it more precisely to determine this ID-VD characteristic. So we have the current and then the voltage equation, which the full ID-VD characteristic ID-VD, and then we consider as a different VGS here. So the previous graph we only show the one curve which is under one gate bias. So that's a one gate bias. But in the end, we actually will be interested in the multiple gate bias characteristic, which will be shown here. So this is IDVD with the increase of VGS here. And then the different VGS will cause a different VDS set, which we might have here, 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 here. So that's a different VDS set. Because the VDS set is equal to VGS minus VT. And we have a different VGS for sure that we will lead to the different VDS set. So therefore, we can still define this region as a saturation region. And this region is a linear region. So the general equation for the non-saturation region or linear region is shown below, where we have the drain current is equal to our channel width times our mobility mu n times our oxide capacitance over 2 channel lengths and times 2 VGS minus VT VDS minus VDS square. So that's the current equation for linear region. And the current equation for saturation region is equal to ID is equal to W mu n Cx 2L, which is equal to VGS minus VT square. So that's the current equation for saturation region. So if you have followed the basic electronics, that should be the typical equation you have learned from the basic electronics. So that's a general form, and the next stage that we were going to derive this equation. So when we try to have a certain derive for this equation, we have several follow assumptions. The first one is the current in the channel is mainly due to the drift rather than diffusion. And there's no current through the gate oxide. And then the gradual channel approximation is used, and this approximation means that the electric field in the x direction, Ex, is essentially as a constant. And any fixed oxide charge is equilibrium charge density at the oxide semiconductor interface, and the carrier mobility in the channel is also considered as a constant. So these are the assumptions that we needed for the later to estimate, to derive this current IDS VDS equation. So let's start to go to the one by one. So for this equation derive that we just follow the very simple rule. First one, we assume there is a ohmic from the very basic Ohm's law, where our current is equal to such like this one, with the resistivity times the electric field. And also, one thing want to remind that this is a schematic of the one MOSFET, but now we define as a L and W here, where W is a channel width, and the L is a channel length. So we have the current equation, where is the integration of the Jx along dy dz, and we also have the charge can be estimated by this, and in the end we lead to the current equation is equal to minus W mobility times the inversion charge Qn plumb times the electric field. So now we consider as the charge neutralities, because of in this case this is a charge distribution in the n-channel enhancement mode MOSFET when VGS larger than threshold voltage. So our Qn plumb plus a QSS plumb plus this one and this one will be equal to 0 due to the charge neutralities here. And also we consider the Gauss law, where integration of this term will be equal to the Qt, which is the total charge density enclosed by this interface. So the En is an outward direct normal component of the electric field across the surface of the S here. So the surface 4 is only the surface that contribute here. So therefore, by consider this fundamental equation which equal to Qt, finally we can have this result as shown in here. So that's lead to this equation. So then we just try to put whatever we know so far. So the first one is the EFP minus EFM. The EFP minus EFM will be equal to VGS minus Vx here. And VGS minus Vx will be also equal to this term. And therefore, the VGS minus Vx is equal to Vx plus 2 phi Fp plus a phi s. So this is taken into account as a metal semiconductor Wolf function, and phi s equal to 2 phi p is the condition that reach for the inversion, where we have been already derived in the previous lecture here. So now we also can have the electric field in the other side just equal to the voltage divided by the thickness here. So therefore we have this term, and also is equal to this one. And from the previous slide we have been shown this will be equal to this one. So the Qn is here. So finally we can have the current equation as shown in here. So the last step is we will do the integration of the Ix along 0 to L, and we just put everything what we have been known from previous line, and we consider now the drain current is equal to minus Ix, and therefore with this consideration, then in the end we will have the current equation. ID is equal to W mu n Cx over 2L and 2 VGS minus VT VDS minus VDS square. So this is an equation where we have been already shown in the previous slide. So if you try to plot this equation, then you will realize that this equation actually is shown as this kind of a characteristic, which now physically we know it might not be the true, because after the VDS set, we expect to see as a saturation current here. So therefore, the value at the VDS at the peak current value can be considered by this one, and where our VDS is equal to VGS minus VT. And therefore, with all these consideration, we can start to rewrite this equation. In the end, become this one. So therefore, we can have the saturation current equation from here. This is a saturation current equation, and this is the linear current equation, which is here. So basically, the derive of this equation is not that spatial, just follow step by step, and then the textbook are all explained very detailed. So how this equation derive. So one thing is interesting to know that if we have this current equation, once we convert as a very small VDS, we consider small VDS here, then we can simplify this equation, become like in this way. And then if you try to plot as shown in here, and then the first one is from the ID VGS with a very small VDS, we can have this slope, which will be equal to this term. So the extrapolation of a straight line to the zero current gives us a threshold voltage. And the slope is proportional to the inversion carrier mobility here. So by considering the ID VGS, we can get the VTH and also the mobility. But if you consider as a square ID versus the VGS, we can also have the slope, which is also related to the mobility as well. So the same ideas can be applied to the P-channel device, and then the only difference is now we have a VSD and VSG here. So that's all for all the current equation. ID is equal to W. But now we have to consider the whole mobility mu p Cx over 2L. And this will be 2 VSG minus VT. VSD minus VSD squared. So that's a p-channel device for the linear region and saturation region. Which is equal to this one, which is a W mu p Cx over 2L VSG minus VT squared. So that's a ID set. So it's a very similar. Just put as a VSD and VSG here. So here is a very simple example to let you have a rough idea that how are we going to use this equation. So this is a design of width of MOSFET such as specific current induced by a given applied bias. Consider an ideal n-channel MOSFET with a parameter, such parameter of the channel length, mobility, outside signaling, outside capacitance, and threshold voltage. And in the end, we want to design the channel width W such that can have such current, saturation current around 4 milliamp at the VGS equal to 5 volt. So the idea is very simple. We just put the equation, idea set. ID set is equal to this one, where W mobility Cx 2L VGS minus VT squared here, and then just put all the number here. We have a 4 milliamp. We have the mobility 650 and Cx 6.9 times 10 to minus 8. And L is a 1.25 micrometer. And VGS equal to 5 and VT equal to 0.65. So then that's a very simple calculation. So you got the W equal to 11.8 micrometer here. So in the end, this question is become actually very useful design, because that's how actually the reality design question that will be faced day to day, because we will be always want to design the transistor that fit our spec. So this question is actually, although it's simple, we have a source and drain, we have a channel length, .25 micrometer. So therefore, to make sure that this transistor can deliver the current reach our target, so the question is common and useful because this is a typical when we try to design the layout of our transistor, we will face these issues because we don't know how large of W should design. And then normally when we design the layout of the transistor, we won't look at the cross section, we only look at from the top view. So if you look at the top view, this is you view this from the top. So then you will only see your design tool, especially for the layout design, which will be a bunch of the square. So we will mainly design this square, which is a W here. And this blue square, which is normally considered as a gate electrode. So this is what we are doing day to day to design the layout. So if you want to fabricate a transistor that can deliver a 4 milliamp, what you need to normally, the only things you can design it probably will be just try to design the top gate metal, and by consider the different widths in the end to make sure that this width can reach to this dimension that can give us enough current here. So this is a top view of this MOSFET. So the next is we will introduce the transconductance, which is a very important parameter in the MOSFET. So the MOSFET transconductance is defined as a change in the drain current with respect to the corresponding change in the gate voltage. So the equation is shown here. Transconductance is defined as the derivative of the drain current over the derivative of the gate voltage. So this is how this sentence suggests the change in the drain current, this one, over the change in the gate voltage, this one here. So that's the basic definition of the transconductance. So the transconductance is sometimes also referred to as a transistor gain. And in the non-saturation region, linear region, we just put our current equation, the derivative of a current equation in linear versus a VGS. So we can have here, the W, mobility, Cx, VDS, channel length. And in the saturation region, it's a W, mu and Cx. Over L times VGS minus VT. But the most important learning here is not related to this equation, because this equation just put whatever we have, just put a simple derivative. But more important is try to understand what's the physical meaning of this transconductance. So if you try to look at this transconductance, it's a derivative of ID over derivative of VG, which means if you closely think about this as a IDVG characteristic, we have the IDVG curve like this way. But now if you try to plot as a transconductance versus a VG, what would be the curve look like? So we have the GM versus a VG here. So the derivative of ID over VG in the end will become the curve as still once the threshold voltage, gate voltage larger than threshold voltage, we start to see the transconductance increase, but that will drop. Why that will drop? Because now we reach to the saturation. So this will also drop here because of the current between here and here is getting less and less increase. So we will see the current drop. So that's from the one IDVG curve. But on the other hand, we can also understand from the IDVD curve, we should also understand how this IDVD curve reflects the characteristic of the transconductance. So you have IDVD here. So now we all know that the typical IDVD curve could be like this one, and this one. So each IDVD has a one ID0, right? Based on the one VG0. And the next is ID1, ID2, ID3. But that all need a one specific gate bias, which is VG1, VG2, VG3. But now you think again, the definition of transconductance is the change of the drain current versus the change as a gate voltage. And therefore, if you try to estimate the difference of this one, which is ID1 minus ID0 over VG1 minus VG0. So what does this calculation tell us? This calculation is the same as this one, right? Just calculate as a current difference, derivative of current versus derivative of the VG. So which means the amount of a current increase here is exactly the transconductance. So that's actually is more important than the equation, because the equation just give a number, but it's more important to understand the physics here. This kind of physics that no one tell you in the textbook. This physics is some of the experience we learn from the lots of data analysis. So in the end, you will find out that normally this is transconductance 1, and this is transconductance 2, and this is a transconductance 3. So now you will see in most of the case, when we increase the Vg, the transconductance is reduced. So this is exactly consistent with this curve. This curve also suggests increase the Vg, transconductance will reduce. So which means as long as a higher Vg, your transconductance was getting lower and lower. So therefore, to try to make the good MOSFET, there's one important research direction is how to make the transconductance will not decrease that fast. People want to have the current IDVD. If we can make the transistor as a transconductance always increase without decrease, which means we can make this one always as larger as possible as we increase the gate voltage. So that's also the one of the very important research direction, because most of the case without carefully optimize, the transconductance is always decreased at the high gate bias. But then if you can find a way to increase the transconductance under the high gate voltage, that would be the important breakthrough. That's also the many people work on these fields. Okay, so we will take a short break and come back later.
那个交回去的考卷是什么时候会？
我们会再找时间，再通知大家去确认一下。
好，谢谢。
请问一下，期末考大概会考到
全部考，
好几次
对，就考到 BJT 一定考，
你这个
对，一定会帮我列到 BJT。
好，
对。Okay, so for the MOSFET operation, in previous case, we always consider the source grounding and the body grounding, so the source and body are the same bias. But in reality, sometimes you will be interested in trying to look at that. How about if the substrate has additional bias? So if we have the additional bias in the body, so that means that when the VSB is larger than 0. So this is typically what we call as a body effect. So when VSB is larger than 0, the service will still try to invert when phi s equal to 25p. However, these electrons at a higher potential energy than other electrons in the source. The newly created electron will move laterally and flow out of the source terminal. So once we have the additional substrate bias, in the end, we will have to consider the band diagram as shown here. Then the service potential here is not exactly equal to 25p anymore, which is equal to phi s is equal to 25fp plus the additional substrate bias VSB here. So that's a main difference between the substrate without bias and with bias. With bias, then we have to consider this will influence our service potential as shown here. So therefore, this influence on the service potential for sure will also in the end influence on our threshold voltage. So therefore you can see from this slide, original, we only take into account the 25fp here. But now we have to consider 25p plus the VSB, and therefore the delta threshold voltage, which will be equal to this minus this. So it's a main difference between the one without substrate bias and the one with substrate bias. And we define this as a body effect coefficient, and therefore the delta VT, which is equal to this one to 25fp plus a VSB minus 25p. So that's with additional substrate bias that will cause a threshold voltage difference. So another very important technology that we were from the beginning of this typical MOSFET. After we have the evolution to this, what we call the complementary MOS, we call the CMOS, where the CMOS is a combination between a MOSFET and P MOSFET. And there are several different possibilities to make the NMOS and PMOS side by side together. For example, like the figure A or figure B. Or the figure C. So the most important that we need to have is this NMOS and PMOS is because in the end, we consider this CMOS, we can make it as a CMOS inverter, which is a basic for CMOS digital logic circuit. So the typical inverter has this kind of the circuit connections, where we have PMOS and NMOS. So the top one is typically as a PMOS, the bottom one is a NMOS, and we connected the gate together, we connected the output together. So we have a one V in, one V out. So by considering this structure, we can realize the inverter, which means in the logic consideration, we give the 1 as a signal, then we will output as a signal as a 0. We give the 0 signal, we will output as a signal as a 1 here. So that's a complementary for this is for the CMOS that we can realize this CMOS inverter. So here is some more details, just similar. We have the PMOS and NMOS. So in the top we have a PMOS, NMOS here, and we connect it as the same output V out and same input as a V in here. And just from this consideration, we have the source. In the PMOS, this is a source, gate, drain, and in the NMOS, this is a drain, gate, and source. So by considering this structure, we are able to realize as an inverter, where the typical logic function for the inverter is we have the signal, also V in, and then we put as a 1 0 1 0. And then in the digital, as we put as a high, that we consider as a 1. We put as a low, that we consider as a 0 here. And by using this inverter, we will have the V out, which is So we give the 1 in the input, we can have the 0 in the output. We give the 0 in the input, we got the 1 in the output. So to understand this operation is also very simple. When we have the V in larger than VTH in the NMOS, therefore our NMOS will turn on. And therefore our VOut will be connected, will be as a signal, as a ground. So therefore, if this is a 1 and we have this as a 0 here. So that's a very simple operations. So finally, let's look at some of the recent literature. This is a paper published in Nature in a while ago, but at the moment it's already demonstrated that this 2D transistor, molybdenum disulfide transistor with a 1 nanometer gate length. So this is a paper published in the Nature, so it's also worth reading. Just the conclusion is that they want to demonstrate that with the MOS2, which is a 2D materials with even downscale down to the 1 nanometer, still can exhibit it as a functional transistor MOSFET characteristic. So the first few sentences, scaling of silicon transistors predict to fall below 5 nanometer gate length because of a severe short channel effect. As an alternative to silicon, certain layer semiconductors are attractive for their atomically uniform thickness down to a monolayer, low dielectric constants, and large band gap, and heavy carrier affecting mass here. So that's actually the background information introduction. So these all just try to illustrate some background information. And then after the background information, this paper starts to go straight to the point. Mentioned here, we demonstrate this MOS2 transistor with a 1 nanometer physical gate length using a single wall carbon nanotube as a gate electrode. So that's a main objective for this paper. So this ultra short device exhibits excellent switching characteristics with near ideal of the substrate swing. So I believe that you have followed this course so far, even if you don't understand this MOS2, the property of this MOS2, but you can understand the main result for this paper is to have the substrate swing around 60 millivolt per decade. That's where we already mentioned previously, and also the on-off current ratio up to 10 to 6 orders. So therefore, this paper try to demonstrate the SS can achieve 65 millivolt per decade, and also the on-off ratio can reach 10 to 6. So these two characteristics that we have been already taught in the first class a long time ago in the September, in the first class, in the February, now it's May, so sorry, it's in the March or February, in the first class, we already talked about the key result for transistor is the on-off ratio and substrate slope. So this paper, they just try to demonstrate. If you try to plot log ID versus VG, so this paper, without looking their characteristic from the text, we can already expect what could be the result from this paper. They have the SS roughly around 65 millivolt per decade, and also the on-off ratio can reach up to the 10 to 6. So that's actually just the first paragraph of this paper. This paper is not that long. It's worth reading. The rest is some more detail. This just to show you that the knowledge that you have now is enough to understand this paper. So from the first paragraph, we can already foresee what will be the key result from this paper, and the rest just the details. So if you look at some key figure for this publication, so we can see that from this publication, for sure, normally they will show the device structure. So this is their device structure. We have the source and drain here, and then they try to use a carbon nanotube as a gate. This is the single wall carbon nanotube. So they try to put this as a gate. This is a gate. So they apply the VG here, and then this is their channel length. Can be dumped to 1 nanometer. So this paper just want to demonstrate that it's always a rumor that we cannot continue to do the scaling, because beyond a certain dimension, we have very serious short channel effect. We got lots of problem. So this paper just fundamentally demonstrates that still, as the channel length down to 1 nanometer, we can still see the very functional transistor behavior, very functional MOSFET behavior. As you can see here, this is a functional MOSFET characteristic, where can reach for 65 millivolt per decade, and good on-off ratio, good output current, and then also the low off current, and also can see this as a functional IDVD characteristic. So with all the knowledge you have now, is enough to understand the key result for this paper. Okay, so that's end of this. So the final is the key summary that for this chapter. So we talk about the MOSFET is a voltage control device, and we have a gate voltage modulated channel charge, and the inversion layer is a key conduction path is formatting when the VG is larger than VT, and the drain current is mainly controlled by charge and electric field, and we have the linear region and saturation region, and also threshold voltage is very critical, and in the end the capacitance interface effect also plays a certain role to determine the MOSFET behavior. So that's the end of this chapter. So we'll move on to the next one. So since we complete the basic for the MOSFET, so we will move to some additional concept for the MOSFET. this additional thing is the sum of the non-ideal effect that we should be aware of, because that in the end will be the main challenge for the continue to improve our MOSFET characteristic. So first of all, we need to understand certain non-ideal MOSFET behaviors. For example, the substrate conduction, mobility degradation, channel length modulation, and also we need to understand the short channel effect and how this short channel effect impact on threshold voltage and device scaling. And also there's a certain phenomenon that we call the velocity saturation and ballistic transport. And also we need to understand the basic scaling principles, and in the end include some of the reliability and breakdown mechanism. So this is something that crucial for to understand some of the additional concept for the MOSFET. In fact, this chapter is very important for your future research and work direction, because nowadays we just try to solve. When we do the more scaling, when we have a new transistor, new material, new scaling, new architecture, what we need to face is just try to solve, understand, and solve these additional effects. So the first one, substrate conduction. So in the previous chapter, we only considered that the current will be formed when VGS is larger than VT. But in reality, even when VGS smaller than VT, there's still a current that we call as a substrate current. So if you try to look a little bit closely for ID VG characteristic, and then you try to plot as a log ID, so you will find out that even we define a threshold voltage as here, and below the threshold voltage, we still see a little bit amount of current, and this is because due to the substrate hole conductions here, substrate hole current here. And this can be also understood by several different aspects. The first one is that the Fermi level is closer to the conduction band than the valence band, as shown here. So now your Fermi level is already close to the conduction band and far away from the valence band. So this close to the conduction band suggests that this region is already as a lightly n-type. So the semiconductor service developed the characteristic of a lightly doped n-type. And also, although it haven't reached the condition of 5S larger than 5P, but this condition 5S below 25P but still larger than 5FP here can be considered as a weak inversion. So for CV characteristic, if you go back to the chapter that we talk about CV, we also talk about the region where we call as a weak inversion and strong inversion. And the weak inversion is already that the semiconductor service become the lightly doped. So in that case, that we start to foresee there's a little bit amount of current at this condition, and therefore that's we call as a substratal current, because the current is happen below the substratal hole condition. So we can also understand from this aspect. So this is a Venn diagram from the source to the drain. So this is at the without any bias. Now if we consider as a VG smaller than 0. So the VG is smaller than 0, so we will increase the barrier. So the electron is not likely to jump from the source to reach the drain side because of a large barrier here. But the previous one, we say the electron can be conducted is under the case with the VG larger than VTH. So then your barriers high is reduced, so the electron can start to travel from the source to the drain. But in the case here, VG is larger than 0 but smaller than VTH. But in this case, the barrier high is already reduced, so therefore the electron might start have the chance to a little bit overcome and reach to the drain side. So this can be also used to understand the substratal current. So here's some of the experimental result. You can see that below the threshold voltage, this is the threshold voltage. So threshold voltage around 1 volt. Below threshold voltage, we can still see the current here. Although it's not that large, but at least this is a certain amount of current still exists below the threshold voltage. So another very critical non-ideal effect is the channel length modulation. So when the MOSFET is biased in the saturation region, so now we all knew that the depletion region at the drain terminal extend laterally into the channel region. So you will have the larger depletion width here. So your VDS increase, which means your depletion width increase. And then your depletion width increase, which means this delta L is increased. So then the affected channel length will be reduced because of the channel length is equal to L plumb is equal to original L minus delta L, right? So now your delta L increase, so your affected channel length reduce. So that's how we call the channel length modulation, because your affected channel length actually in the end is reduced. So we can consider this is a typical depletion width equation, but now we consider the additional one due to the VDS. So the delta L can be estimated from here. And because of our current is also proportional to our channel length, so therefore, if the delta L is increased, which means our channel length is reduced, and then our ID prime actually is increased in the end. So we can also put this correlation into our original current equation. In the end, we can define as this additional factor called the lambda here, where is the channel length modulation parameter. So in the end, what actually the influence on our ID-VD characteristic? So imagine you have an ID-VD characteristic. So from previous chapter, we have been know you should have the linear saturation. But now if we try to consider the channel length modulation, actually you will see the less saturation, which the curve will become like this one. And this additional current increase, which is because due to the effective channel length reduced because of a delta L increase. So this effect that we call as a channel length modulation. So once you see the channel length modulation, you will see the non-saturate of an ID current. Some non-ideal effect is also related to the mobility variation. So when we consider the ideal IV characteristic, when we try to estimate the ideal IV characteristic, we assume that mobility was a constant. However, this assumption must be modified for two reasons. The first effect to be considered is a variation in mobility with a gate voltage. And this is because that when we apply the VGS here, and that actually we will start as we foresee that we will have the formation of the electrons here. But not only this electron will be influenced by VDS, because of the electron will flow to the drain side due to the VDS, but the electron will also be attracted by the gate voltage here. Because you have the positive gate voltage here, so the electron will also try to inject upwards. So therefore, this will influence the mobility by considering different gate voltage here. And another influence is because due to the surface scattering. So once you have the lots of defects in the semiconductor between the oxide and semiconductor interface, so the electrons might start to be trapped at this interface. And these negative electrons, this is trapping electrons due to the interface state. So this trapping electron also will cause a little bit repulsive force for our conducting electron, because this is a negative charge. And then the channel floating here, the electron, still will be the negative charge. So once you have the negative charge close to the another negative charge, for sure you will induce the Coulomb repulsive force. So this negative charge will try to push the surface conducting electrons away, and that will cause the electron degradation and mobility degradation, and that's we call the surface scattering. So once we have a surface scattering, we see the degradation of the mobility. So that's why to optimize the interface, to reduce the interface state is crucial, because in the end, this will influence our performance, especially related to mobility. Once we have a low mobility, for sure we have a low current here. And the second reason for mobility variation is that the effective carrier mobility decrease as the carriers approach to the velocity saturation limit. So normally, if you try to plot as a mobility versus electric field. So originally we expect the large electric field, large mobility, but beyond a certain condition, we will see the saturation here. So this is how we call as a velocity saturation. So here's some more details about velocity saturation. The carrier velocity increase until the ideal current is attained. However, we have seen the carrier velocity saturate with increasing electric field. Velocity saturation will become more dominated in short channel device. So the short channel device means that the channel length is small. And because of since we apply the same drive bias in the drain side, if the channel length is reduced and then the effective electric field is become larger. So the velocity saturation will occur when the horizontal electric field is approximately reached to 10 to 4 voltage per centimeter. If VD is 5 volt in a device with channel length of 1 micrometer, that will reach the 5 times 10 to 4 voltage per centimeter. So therefore, velocity saturation is likely happen. So if you have the 1 micrometer channel length device, as long as you apply the 5 volt, that already reached a condition to trigger the velocity saturation. So once we have velocity saturation, we also need to consider that the revise of our saturation current ID set is equal to WCX VGS minus VT V set. So that's how this saturation velocity influence on our current here. So here's some more experimental results. So you can see on the left hand side you have a different materials that versus electric field, and in the end it all reach as a certain saturation in somehow. So that will cause the current cannot be continuous increase as we increase the drain bias. And if you see the right hand side, it's important to consider this velocity saturation, because then we see the highly reduced of our drain current, which is very important for us to modeling and also take this into account for the current driving capability. So the next non-ideal effect is how we call the ballistic transport. So the average drift velocity is a function of the mean time between collisions, or the mean distance between scattering events. So in the long channel device, the channel length is much longer than the mean distance between the collisions, so the average carrier drift velocity exists. As the MOSFET channel length is reduced, the mean distance between collision might become comparable to L, so that the previous analysis might not be valid here. So if the channel length is further reduced, so our channel length is smaller than our L, which is a mean distance between the collision, then the large fraction of carrier could travel from the source to the drain without experience a scattering event. So this phenomenon is how we call as a ballistic transport. So let's just put some numbers, probably you will get some more sense. If you consider the small L, which is equal to 1 micrometer, which is the mean distance between the collisions. But now you fabricate a transistor that had a channel length of 50 nanometer, which is smaller than our mean distance. Therefore, in this condition, the electron can travel through the channel without experiencing any scattering event. That's how we call as a ballistic transport. So the next concept we will consider is the MOSFET scaling. Scaling definitely is one of the most important consideration if we want to push the semiconductor for the next generation. And in the early time, we consider as what we call the constant field scaling. So the principle of a constant field scaling is a device dimension and device voltage to be scaled such that the electric field, both horizontal and vertical, remains essentially constant. For example, you consider as a VG as a 5 volt, and you have a channel length, you have oxide thickness of 10 nanometer, channel length as a 1 micrometer, and substrate doping is a 10 to 17. And then with a constant field scaling, we consider the factor around 0.1, and therefore we can have the 1 nanometer. This is by consider as a K constant K value 0.1 scaling. So in this case, we can make as a 1 nanometer oxide thickness, but the channel length will be equal to KL, which is a 100 nanometer. And the voltage can then be reduced to the 0.5 volt. And also, to reach this one, the substrate have to be 10 to 18. So that's what we call the constant field scaling, because if you try to estimate electric field on the left and right hand side, they are actually have the same electric field. So here is some more information. The typical value for this constant field scaling for each generation is around equal to 0.7. So if you look at the one of the critical consideration for the scaling devices, which will be the short channel effect. So in the case of a short channel effect, the space charge region, we already knew that space charge region in the source and drain will extend into a channel region, but occupy only a small fraction of an entire channel length. So this is a typical case for the long channel device. So in the case with long channel device, the depletion region here will only occupy a very small fraction of compared to the entire channel length. So you have a channel length here. So this is WSP. This is WSP here. Now the WSP is much smaller than channel length, so therefore we won't see any influence here. So once we bias this MOSFET being as an inversion conditions, so we will see this is our charge here. The inversion channel still will be is mainly controlled by the gate. On the long channel device, we have a depletion width from the source and drain, but this depletion width will only take a very small fraction compared to the whole channel length, so therefore the channel still will be mainly controlled by our gate bias. But imagine if we try to make it as a very small channel length device, then we will see the fraction of the charge in the channel region controlled by the gate now will reduce. So if you look at the right hand figure where we have a small channel length device, so our depletion region has been extended to this part and this part. So now this is our WSP, but our channel length controlled by the gate are only left as shown here. So which means that the inversion channel now cannot be fully controlled by the gate. And that's how we call as a short channel effect. So this slide just shows some the analytical calculation in the end to calculate the difference between the short channel and long channel. So we won't go into the detail, we just show that the calculation shown me here that can be estimate the voltage difference, the threshold voltage between the short channel and long channel device. And also, this is one example. You just put all the equation there, you will be able to find the threshold voltage shift due to the short channel effect. So in the end, we will see that the channel threshold voltage is decreased around minus 0.0726 volt. You can try to calculate by yourself and you will get these numbers. But the most important the characteristic phenomenon you have to know is about this figure, because the left hand side is a very typical classical characteristic that once we have the short channel effect. So once we reduce the channel length from 5 to below 1 and we see the threshold voltage will reduce. So the VTH is decreased, and this phenomenon, channel length decrease, VTH decrease, this phenomenon also we call as a threshold voltage roll-off. And this phenomenon will become more obvious in the case with a larger drain bias. And why larger drain bias will make this worse? Because the larger drain bias, you get longer depletion region. You have a wider depletion region between the drain to the substrate. So therefore, your channel is less controlled by the gate anymore, and then you will see more impact that the ones we have the VDS is a small bias is a large, that will cause more negative shift of our threshold voltage. So additional concept similar to the short channel effect is that we call as narrow channel effects here. So the narrow channel effect is very similar to the short channel effect, but just consider as additional space charge region at each end of the channel width. So this is another consideration. This is a channel length. And now we also need to consider the additional space charge region at width, at the end of the width here. So the additional charge is controlled by the gate voltage, but not included when we calculate the ideal threshold voltage relationship here. And with all these calculations, in the end we got the conclusion the delta VT will have a certain correlation with our channel width as shown here. So once you see these characteristics, where is the threshold voltage versus the channel width, then we see the channel width become smaller, our threshold voltage become larger. And then in the end, this is a conclusion between the short channel effect versus narrow channel effect here. So short channel effect sometimes we also call as a SCE. So the SCE will cause the threshold voltage reduce. Also in the end, because the threshold voltage become more negative, so in the end lead current can be increased. Because right now we have a more wider depletion region, so lead current can be increased. And then that's why we need to have the SOI or FinFET, such advanced architecture to reduce the short channel effect. So I hope to finish this chapter today, so I will continue. So then the additional electrical characteristic we will talk about is oxide breakdown here. So in the previous case, we only consider the oxide as an ideal case that we won't have any lead current. But in reality, we will always see the lead current. So that's how we call as an oxide breakdown. So if the electric field in the oxide becomes larger enough, the breakdown can occur, which can lead to a catastrophic failures. So here is a typical example that whether we see the IG versus the VG at this point, and then we try to sweep till as high as possible, then we see the gate lead current increase. And once we see the gate lead current increase, that means we will see until this point, we see the breakdown happen. That's a dielectric loss, the insulating property. The dielectric will lose the insulating property. So that means our dielectric is no longer as an insulating material. So this is what we call the oxide breakdown. So this is a phenomenon that we have the oxide breakdown. So the oxide breakdown not only is related to the bias, but also is related to the time. So therefore, there's a very well-known reliability issue that we call the time-dependent dielectric breakdown, TDDB. So if you look at this graph, where the y-axis is a gate current, the x-axis is a time here. And if you bias at the one fixed gate bias, for example, at the 10 volt, it could be in the beginning we have such stable lead current, but after a moment we see the current drop in the end to reach to the breakdown condition. So therefore, that's what we call as a time-dependent dielectric breakdown. We won't talk the reason, the physics here is related to the reliability. Lots of interesting physics that we can use to understand this phenomenon. So but we won't talk this in the detail. And another typical breakdown is what we call the average breakdown. So the average breakdown is mainly because if we have the VD is larger enough, so if we have a larger VD, that can trigger as an average breakdown. In the previous, when we talk about the diode, we already talked about the average breakdown. So similarly, in the diode, we have mentioned in the PN junction, we have been already mentioned this is IV, and then we have a forward, and we have a reverse, and as long as we apply enough reverse, we will see the breakdown, and the mechanism lead to the breakdown is what we call the average breakdown. And this happened for the PN junction under reverse bias, and also this under the MOSFET bias in the drain side. This is reverse bias for PN junction. So we still have a reverse bias in the PN junction, so we can expect that should have the average breakdown, the same mechanism happen in the drain side. And the only difference is that if you look at the IV characteristic, so you look at the ID, VD, once we apply enough high drain bias, we see the currents going. That's because of average breakdown. This is happen at the VG equal to 0 volt here. So that's the average breakdown. But the idea, the concept is the same like the PN diode. And another very well-known breakdown is what we call the punch-through effect. Especially this is very important for the short channel device. So the main reason is that once we have a short channel device, so the left figure is a typical N from the source to the drain. This is NPN. We have N plus, PN plus. And then because it's long channel, so the electrons here is difficult to jump over the channel, reach to the drain side. But once we have a short channel device, actually the barrier here is reduced. So that's the electron is getting more easily to jump across this barrier. This is consideration of a large drain bias. So therefore, you will see this kind of a typical IDVD characteristic where we will have the high leakage current. This is a case at the VG at the 0 volt. We will have a high leakage current, and also we won't see any saturation region. So the punch through is mainly due to the drain to substrate space charge region extends completely across the channel region to the source to the space charge region. So therefore, we will see this kind of short channel effect. And one possible interesting design is that we will make as a lightly doped drain. That's we have this what we call the LDD. Because the junction breakdown is mainly happen due to the its function of a maximum electric field. As the channel length becomes smaller, the bias voltage may not be scaled down accordingly, so the junction electric field becomes larger. As the electric field increase, the near average breakdown or near punch-through effect become more serious in the higher electric field. So therefore, we will normally try to design as a transistor where we call the lightly doped drain here and here. And then to understand this in the very short way is that the LDD can reduce the electric field as shown here. So once the electric field reduce, then we can avoid the breakdown. So LDD can reduce the peak E field in the drain side. And another is normally what we do is by consider as an additional implant to adjust the threshold voltage. Sometimes we don't have our expected threshold voltage because due to limit by the substrate doping, but we can consider as a adjust. We can consider use implant to change or adjust the substrate doping. So the idea is simple. We just make it as an additional doping concentration due to the ion implantation. So then we can adjust our threshold voltage as a D1. Show me here. This is mainly contributed by the implantation. So the last one, the non-ideal effect, is how we call the hard electron effects. So as a electric field in the drain junction space charge region increase, we will start to see the electron hole pair can be generated by the impermeabilization. So this is condition we have the VGS but also VDS at the same time. So once we give us a large VDS, we will see that it's possible to have the impermeabilization on this region. So the generated electron tend to be switched to the drain, and generate hole will be switched to the substrate in the channel. So you will have the electrons being injected here, and that will cause a certain additional non-ideal effect. Some electrons generated in the space charge region are attracted to the outside. And these generated electrons have an energy of far greater than the thermal equilibrium value. That's thermal equilibrium value. So that's what we call the high electron, because it's being accelerated, being have more energy, and this will energy electron will across this silicon oxide interface, and then generate this additional interface state. And the probable cause of interface state generation is due to the breaking up of this bonding that create more dangling bond, which acts as an interface state, and therefore we will have the charge trapping in the interface state cause the threshold voltage shift, additional scattering, and reduce mobility. So in the easy way to understand, we will see the electron trapping at this region. So once we will see the electron trapping, we will see all these side effects that will happen. Okay, so that's a key to takeaway. I think everyone can look at by yourself. So that will be end of this class. Just one reminder that we won't have the class on next week because I will be out. So we will see each other at 2 weeks later. And then next week, we will set the another 1 hour that if you still want to check your midterm exam. Some of you didn't take back, and some of you, if you want to look up whether your request for the scoring has been put in or not, so you will be assigned as one specific time, which will be the 11 a.m. on the next Monday. So we will make an announcement for this.